attached at this point? 2. Hybridization? sp2. Hydrogens attached at this point? 2, 3, 2. More people going with 2. Any other suggestions? 1. 1? Oh, I didn't mean it to be that I tried to be. Oh, I broke the pen. It's working. That's the managed to break it. In teaching assessments one year, somebody did complain and say, Dr. Trellick was always throwing pens about. That's the correct answer. Super duper. Good man. If we look at this position here, okay, if it was, so I'll draw it as a carbon atom itself. So there's a bond down there, a bond over there. If it truly was 2 hydrogens, what would be the formal charge of this carbon? Neutral. Is it neutral? No, it's positively charged. So there's something else going on. It's not a normal connectivity. And play around with the options. If there wasn't a bond there, now the carbon atom controls just 1, 2, 3 from 6 electrons. 3 when it should be 4, and would give that positive charge. So we've got a carbon here in the structure, positively charged, because it doesn't have an octet. Okay? So think about the connectivity, think about octets, but also think about what charges are telling you. And if you play around with all the alternatives, it will be just one possible answer for connectivity and charge that can be correct. For example, couldn't be that we have got a lone pair in the carbon that hasn't been shown, because sometimes they leave the lone pairs off. Couldn't be like that, because then the carbon would control 1, 2, 3, 4, 5. And it would have a -1 charge. So again, even though it's a little bit more difficult, we're being a bit more sneaky, when we see those charges, there's only going to be one possible answer between bonding pairs and lone pairs, or missing pairs of electrons for that atom. Formal charge knowledge allows us to work out what's going on. So, this pure carbon atom has a atomic orbital which is empty. It's still sp2 hybridized, because we did have one carbon to hydrogen bond in here, and we said for the level of hybridization, count lone pairs and single bonds. So 1, 2, 3 bonds around the carbon. We need an s and 2 p orbitals to become hybridized, sp2 hybridization. So it's still an atom with a trigonal planar arrangement, but that atomic orbital this time is actually empty. And there's atomic orbitals from the sp2 hybridized atoms next door with pi electrons. So the easiest thing we could show is actually those pi electrons moving around to form a new double bond between the 2 adjacent atoms. And the pi electrons are swinging like a gate. They stay pivoted and locked down from that point, and they swing around and form a new bond here. So there's no fantastic jumps of electrons. The electrons don't jump halfway across the molecule. They only jump to their neighbours that they're already connected to. Too far ahead of myself. So a double bond moves across there, and it jumps the charge across as well. Because now that third atom from the left is missing electrons, complete its octet. Again, it shows how easy it is to get messed around. Look at where your arrows are going. That shows you where those new bonds are going to appear. I was still thinking about past the past, which is high, not chocolate. We don't have to stop here. We can do this trick another time. Again, now this bond pivoting from this point, we show another pi bond move. So each time the pi bond swings, one of the 2 atoms is one of the original atoms where the bond was. That bond moves around, pi bond there, and we've got the pi bond in here. So the positive charge moves on to the end of the molecule. So when this bond breaks, those electrons which are needed to fill this atom's octet, the electrons move away from that atom. So we've got 3 resonance structures in total. First one, the bond swings round, plug in this gap. Second time the bond moves, this bond swings around, plug in this gap. So each time we can almost look at it as if the structures are trying to plug in the weakness for the molecule. And it moves that positive charge around the molecule. And if we get into more resonance structures, we stop here for this one, and if we get into more, you see how systematic that movement of the charge is. It goes from there, and pops along 1, 2 to there, and then pops along 1, 2 to there. So the bouncing or movement of the charge is fairly regular in its intervals. And there's the weakness in the molecule. It's that positive charge, that incomplete octet, which makes this molecule unstable. And we can see through resonance how those pi electrons can flow and move around to try and stabilize the molecule. And the more resonance structures that we can draw, the more stable the molecule. So again, with this one, we have a charge on this carbon atom here. And charge on the molecule is often the hot spot, the weakness in the molecule. And the resonance structures show us how that hot spot, either a lack of electron density because of a positive charge, or too many electrons and a negative form of charge, we show through resonance how that weakness, that blip in the molecule is moved around. Moving electrons to fill in octets, and moving electrons to move that negative charge. As atoms with too many electrons are almost as unstable as atoms with too few. So where could those electrons go? Just as importantly, where can't the electrons go? One thing for sure we know each time is that the relative connectivity of the molecule is not going to change. Always going to be, each of our examples of resonance, always going to be 6 atoms connected together in a ring. Don't worry if you're wrong, this is a learning curve after all. So there's the hot spot, there's the potential problem with the molecule, negative charge in the carbon. How many hydrogens are attached at this point? What do you think? Let's look at the alternatives. There's either going to be 0, there's going to be 1, or could there be maybe 2? Let's see if we can find out. If it's 0, then would it give a negative charge in this carbon? It controls 1, 2, 3, 4 of the electrons. That would make the carbon electrically neutral if there weren't any hydrogens attached. But it is charged, it's negatively charged. So that isn't an option. Is 2 really an option? Or could there be 2 hydrogens attached? Make it positive charge. Well, we did make it positive charge. But what's the problem if we put 2 hydrogen bonds in there? How many electrons are in that carbon atom's outer shell? How many does it see in total? 6. 2, 4, 6, 8, and then the 1 pair, 10. Then break the octet rule to have 2 hydrogens attached. Remember, be careful, think about how many electrons belong to that particular carbon, and therefore what's its form of charge. But also remember the octet rule. It should normally be 8 electrons in total around the atom. So we can't possibly have two chemical bonds, a lone pair, and two hydrogen atoms connected to that carbon. Will sometimes be low with empty orbitals, but will never be above 8. Will never go beyond the octet rule for the carbon. So with one carbon to hydrogen bond, it controls 1, 2, 3, 4, 5. One more than it should, and that does give the negative charge. So that is the connectivity around the carbon at that point. Everybody see that? And again, often I find that people, they just get a bit nervous and think, oh well, how am I supposed to know which one it is? It could be a couple of things. But then just run through them systematically and you'll find that only one of them can possibly be right for the charge which is suggested. Always be only one right answer. You're only ever looking at maybe 2 or 3 options at most each time. So you will be able to work it out. So that's the true nature. What about the carbon atom here? How many hydrogens does it have? 2. Has 2. There's no suggestion of charge, so it must be just the normal octet and 2 carbon-to-carbon bonds and 2 carbon-to-hydrogen bonds from that point. So as we move these electrons and try and move that charge around, can we move in this direction? Would that cause a problem if we put a chemical bond here? Again, it's our octet rule. 2, 4, 6, 8, 10. Won't go. The carbon is never going to break the octet rule by having too many. Sometimes it might have too few, and that probably means a positive charge for the carbon. But the carbons and most of our early elements in the periodic table, other than phosphorus and sulfur, they're never going to break the octet rule by having too many. So the only direction in which these lone pair electrons can move is in this direction. That gives the carbon a problem here, but then those pi electrons are going to pop off and appear here. So it's like those first couple of examples we looked at. As a new pi bond comes in, a pi bond has to break. So now our structure, bond there, bond there. There's a lone pair of electrons there. That follows the rules about the number of valence electrons. We've got the same number of lone pairs in the structure, and we've got the same number of pi bonds in the structure. They're probably the 2 most important rules. One lone pair in the first structure, one lone pair in the second, and there's going to be one lone pair in the third structure somewhere. Likewise, 2 pi bonds, 2 pi bonds. Our third answer is going to have 2 pi bonds exactly as well. So we can take a step further. That lone pair could move again, and it's always moving to adjacent atoms. That's where the lone pair is. So it's only ever going to form a bond either here or form a bond here. There's no great jumps in logic in where the electrons move. They're always just being passed to their neighbours. The electrons come in, something has to give because it would break the octet rule otherwise. So those electrons pop off into the lone pair once again. So there's a symmetry and there's a flow to how those pi bonds and lone pairs move around the structure.